So trees have the notion of left and right. Okay, so we have a left pointer and we have a right pointer. And that's the calculus in a tree. When searching a tree, we are looking for either is it left of the is the value we're looking for in this node, or is it smaller than this node or larger than this node. So there is this idea of a left subtree or a right subtree. And you'll notice, obviously we have a very shallow tree here. We only have 5 nodes in this tree. However, this value at the left subtree level is in itself a tree. So a tree is made up of smaller trees. Okay, even if it's a single node, it's made up of smaller trees. So in that way, a large tree is composed of smaller trees, and we can break down the search or the insert or whatever into a smaller subset of problems. So number 1, trees lend themselves to recursion. Number 2, trees are often logarithmic in the way that they operate. So because it's a tree, logarithmic, or when you insert a value, it's inserted logarithmically because you're literally looking for just left or right. You're not looking at the entire tree itself. You're only looking, is it smaller or is it larger than my current node? And that's one of the benefits of trees in themselves. When we look at the whole tree, so if we were looking at, here we have values of characters, right? So we have a capital B, a capital F, M, R, and P, right? So here we've added the R first before we added the P. So we added the R, and then when we go and add the P was added after the R, because if the P was added before the R, the P would be here and the R would be to the right. Note that the order of adding does matter in how the tree is ordered. However, it doesn't matter what order you do it, the functionality is still the same, and the speed of both finding a value and inserting a value does not change based on when you actually added it to the tree. So here, even though the M was added first, the F and the B, and then the R was added, and then the P, which would give us this staggered tree structure, finding the P is still going to take us 2 steps, regardless of whether it was left or right. And yes, if the P was added before the R, the P would be found more quickly than the R by 1 step, but it's still the same logarithmic calculation that you need to do. Because this is in essence, a tree is going to give you a binary search and a binary sort in and of itself, based on how it's actually coded. So we have 2 pointers pointing to additional nodes. So this node, unlike the linked list node, which has a single pointer, this has 2 pointers, and unlike the linked list node that is bidirectional, this is a tree pointer, so it has a pointer left and it has a pointer right. And you hit the bottom, quote unquote, when you hit a null pointer. Okay. So if we are adding values, if we wanted to add the value S, for example, we come in here, we look at M and we say, is S greater than M? And it is. So we go to the right and we say, is S greater than R? And it is. And we go to the right and we say, oh, there's a null pointer. So we'll insert S here at this null pointer section. All right. That's how a tree is built. It's built organically, node by node by node. Now, I will tell you, part of the there are a couple of difficulties. You're thinking to yourself, wow, this is amazing. It gives me, I can sort it quickly, I can search it quickly. It's an amazing structure, and it is. There are only a couple of things that are difficult about it. One is rebalancing. So imagine if we had started with M, okay, and we had added L and K and J and G and D and E and A onto this, right? What would we have? We would have this continuous tree down the left-hand side, okay? And basically, all of the lefts would be populated and none of the rights. So the tree would be deep, what it would be very small as far as the width of the tree. It would be deep, but it would be one branch, okay? So there is a notion, once a tree gets to a certain depth of nodes, that it does what's called a rebalancing. So we pick a random node that's in the quote-unquote middle, and we have an algorithm to do that. And we pick that node and we make that node the root, and then we readjust all of the other nodes based on that new root. Okay, so if we, looking at this tree here, if we had, say, L in here and K in here, and we had C and D in here and A in here, and this was, I don't know, 6 or 7 deep, right? Then what we would do is we would pick a value in the middle, say D, and we would bring D back up to the root, and we would rebalance the tree. So this rebalancing is a linear operation. It basically is linear because you use all of the nodes that are available to you, and essentially re-add them with a new root. Okay. In this example, all of the values are letters, but these could be names, right? These could be last names. And again, it could be last name and first name. So again, it could be last name of Jones and first name of Ivan. And to the left, we have last name of Jones and first name of Bob. And to the right, we have last name of Jones and first name of Yolanda. So it doesn't matter how they're organized. All that matters is that your concept of left means less than, and your concept of right means greater than. All right. Note here, if we were adding, here when we add P and we already have an R, first we check M and we see P is greater than M, and then we come to the R branch. The R branch already exists, and we say, is P greater than or less than R? And it's less than, so we attach P to the left-hand node of R and create the P node. Again, it's how trees work. When you're adding or removing values from a tree.